Good afternoon, everyone. Can you hear me? Oh, excellent. Okay, hopefully the slides are coming through okay. Okay, so I checked quiz 4. Looks like everyone took it. 75% of everyone who took it got a 90% or higher, so that's good. Quiz 4 might actually be the first quiz that didn't have any bugs or typos on it. Didn't get any reports of any issues with that one at all. So that's a milestone. Quiz 5 is posted. The next quiz I've already got on Moodle, and it will be due in a week on next Wednesday by 3:55, and it will cover queuing theory. I'm not sure if I'll finish the queuing theory lecture today. I might. If not, I'll finish it on Monday, and of course you'll still have till Wednesday to submit the quiz. So last time I started talking about queuing theory, and I gave an example. But in a cyber-physical system, this is something that would come up if, for example, you had a controller and you had, for example, multiple processes running control processes, and you had just, say, one I2C channel or less I2C channels than you had processes. So they would be sharing the I2C channels, and so there would be probably some kind of a queue there that the controllers would have to share. So that would be an example, in order to send and receive commands from external peripherals or external devices that you need to exert control. A queuing theory is about queuing systems, or a model of a queuing system, which includes both a queue or multiple queues potentially, as well as servers. And so you've got requests that come in, which I call customers sometimes, or requests that come in. They come in in a pattern, according to a statistical distribution. In this case, we're focusing on the exponential distribution. And they are served and they are released, or they leave the queuing system, also according to a distribution. And so our objective is generally, not always, but is generally to find the latency, which was a topic that was important when we talked about control theory. And so what happens in there is that even when the rate at which requests are coming in is less than the rate at which requests are going out, and that's basically a prerequisite. I mean, you can never have requests coming in faster than they're going out. Otherwise, your system will be unbounded. And so even with the assumption, though, that the service rate is greater than the entrance rate, even with that assumption, now you might say, wait a second, I mean, if things are being served faster than they're coming in, not a big deal, right? I mean, they're just, why do we need a queue? Well, it turns out you need a queue, and depending on the rate at which they're coming in and going out, that queue could still grow to be very large and cause there to be a significant delay in the time it takes for a request to go through the queuing system. Now, when you think about that, you're like, it's almost hard to imagine that. Like, why is that? Why would it take a long time to get through if throughput isn't the issue? The rate at which I'm putting things in, the servers can keep up with the rate at which things are coming in. So why is a queue building up? Why does that happen? Well, it happens, and it all, when you have these parameters of the queuing system, that's what determines the size of the queue and the delay. So generally speaking, what you're trying to figure out here is as you increase the throughput, you pay for it in latency. So like if you have a hard disk, for instance, that hard disk may support up to a certain number of requests per second, and the number of requests per second you issue may be well below that. But as you increase the request rate to the hard drive, yeah, the throughput, it serves it, and according to that throughput, the throughput is not reduced. I mean, you get the throughput that's promised by the hard drive, but the time it takes to get requests through starts to lag. The more you increase the rate at which you issue requests. So that's the deal. That's the thing with the queuing theory. And I'm hoping that in this lecture I can illustrate that. Okay, so as I mentioned, it explains basically waiting time. The three most important things you want to know here are waiting time, how long it takes requests to get through the queuing system, also the number of customers that may accumulate in the queue. So that's going to dictate, what the queue size has to be, how much memory you need, basically. And then the idle time of servers, how long you've got servers idle. I'm not really sure when or how important that's probably the least important thing. Maybe, of course, it depends on the application and the situation. But 1 and 2 are obviously important. 1 determines the performance, and 2 it determines the cost, the resource cost of the system, basically. So that's the thing you want to figure out. There's also a distinction. I mentioned that the queuing system includes both the queue and the servers. So when you talk about waiting time, you can split it into time in the queue versus time in the whole system. And then same thing with the number of customers that may accumulate just in the queue or that may accumulate in the whole system. So there's a distinction there. So just keep in mind that the queuing system includes the queue and the servers. So the characteristics include, as I mentioned, the arrival pattern and the service pattern, both of which are random variables. And the number of servers and service channels, we're just assuming, 1 server and 1 service channel. System capacity, for the time being, we're just setting that to be infinite. And then the queue discipline, we're just going to assume first come, first serve. And the number of server stages, which is would be useful if you had like a systolic array of processors, but we're not going to consider that either. So the queue notation is basically a notation that has 5 slots. Each of those slots means something. The last 2 slots are optional. The first 3 are the arrival time and the service time distribution, which each have a different letter associated with them. In this class, we're going to be using the exponential, which is M, so all of our queues will be MM something. But that's, of course, something you can change if you get into queuing theory a little bit more. The third option is the number of parallel servers, which we're just going to consider 1 for this course. Obviously, in many real-world scenarios, you're going to have more than 1 server. I mean, that's pretty typical. So, but those 3 parameters, the first 3 parameters there are the most important ones, and then system capacity, which is the 4th one, which you omit if it's infinite, and the queue discipline, which is the 5th one, which you omit if it's first come, first serve. So in this class, we're going to focus on MM1 queues. Little's law is a very simple law that just relates basically the 3 parameters that I just discussed, which is the arrival rate, the time in the system, which is your latency or your delay, and then the average number of customers in the system, L, which is going to be your needed queue size. Now, one thing too that I'm not sure if I described this well last time, but queuing systems, the whole idea with a queuing, you might think, wait a second, the number of customers in the system, I mean, wouldn't that be dynamic? I mean, wouldn't that just be constantly changing? I mean, sometimes you got 3 customers in the line, sometimes you got 10. I mean, why is there a single value associated with that? Why are you assuming that the number of customers in is a constant? Why is the average time a constant? Well, they're constants because queuing systems are like control systems in the sense that they can become stable. So the assumption in queuing theory, and I didn't mention this last time, but the assumption is that the queue system will become stabilized or will reach a state of equilibrium, or also called it'll reach steady state. It'll be steady state. So when you first start sending customers into a queuing system, yeah, the queue will start out small and it will accumulate customers, and it will be dynamic at the beginning. It will be changing, but eventually it will stabilize. It will reach steady state. So all of the numbers that we're talking about here, that latency and the number of customers, is all assuming that we've run the thing long enough for it to reach steady state. Now that's also assuming that the parameters are stationary, that the arrival pattern and the departing pattern, those are stationary, they don't change. If they change, then obviously there'll be, if you have a non-stationarity in your system, there'll be non-stationarities in the performance as well. But those non-stationarities should all be just temporary, and they'll all eventually lead back to a steady state behavior. So what does that mean? That means if you think of a line, any line that you stand in, as long as the rate at which customers arrive is stationary, and the rate at which they depart is stationary, even if it's random, but it's random according to an exponential distribution, that line will always reach a steady state. It will always sort of stabilize on a certain depth of the line according to the rate in and the rate out. Now, I know for me that's kind of hard to imagine. See, it's hard to imagine that there's some magic number that based on the arrival and the departing rate, that line will be a certain number, but that's the way it works. Okay, so Little's law is very simple. It's just L equals lambda times W. I give you an example here. This is a simple example, mostly because I give you W. W is a given here. Now, normally W is not a given. Usually W is what you're trying to find. But in this case, W is a given because I say, well, it's an elementary school. It takes 6 years to get through it. So W is 6, lambda is 30, and I just want to know the number of students in the school. In this case, it's very simple. It's just 30 times 6, 180. So that's Little's law. Little's law is very, very fundamental, though. As you get into the advanced queuing stuff, you eventually end up coming back to Little's law. Okay, then I talked about the exponential distribution. Kind of interesting. It's basically a thing where with higher rates, you basically are turning down the variance. So if you have a high rate exponential distribution, then the random variable rather, is representing the time in between arrivals. And not only that, but the time in between arrivals is pretty consistent for high rate system, for higher rate system. So if you look at the plot that I have there, you look at that line on the top, which is yellow. The yellow line is very concentrated in the lower numbers, but then if you go lower rate, you go to the blue line, it's a lower rate, it's kind of flat, which means that lower rate systems are basically less predictable. They have higher variance than a higher rate system. So that's kind of interesting. And that's basically kind of an exponential distribution in a nutshell. It has a probability density function that gives you a relative probability, which, as I mentioned last time, is basically a useless number. It doesn't really give you, it's not like you plug in a number and it tells you the probability of hitting that number, because in reality, it's a continuous distribution. The probability of getting an exact value, any exact value, is essentially 0. So the probability density function is really just a relative probability. It's useful for comparing two values, not for giving you an absolute probability. The cumulative distribution function, on the other hand, which is the integral of the PDF, which hopefully you guys remember from Stat 509, that's much more useful. That does give you an absolute probability number, and it's the probability that the value that you plug in is less than, or it's the probability that the random variable is less than the value that you plug in. So, if I put in 2, it's going to give me the probability that the inter-arrival time is less than or equal to 2, of course, given a certain gamma, and gamma is the parameter. And then the complementary cumulative distribution function is literally just, the complement, 1 minus the CDF. So it's the probability that the variable is the value, there's a probability that the variable that you plug in is greater than the sorry, no, that is less than, sorry, the value to plug in is less than the actual value. So the CCDF is basically the area under the curve to the right of the value versus to the left of the value with the CDF. And then I mentioned that the mean is 1 over gamma. So you still have a mean, but the main parameter here is gamma, and then if you want the mean, it's the reciprocal of gamma, and the variance is 1 over gamma squared. So be aware that if I ask you in the quiz or the exam a question with the exponential distribution, I might give you a rate or I might give you the mean. If I give you the mean, then you have to make sure that you take the reciprocal to get the rate gamma. Okay, so here's some examples. So I went through these last time. I'll just cover, let's see, what's the probability of the value being greater than 2? So remember, I said that the value you plug in, I'm talking about this last example here, the third example. So the value that you sort of plug in is 2, but what you're evaluating here is what's the probability that you plugged in is less than the value of the variable, or stated another way, what's the probability that the variable is greater than 2, the value you plugged in? And so you can calculate that. And last time I mentioned that, if you're getting 3 events per second, and it doesn't have to be per second, it's per unit time, depending on whatever unit time you're dealing with. But let's just say events per second is 3. What's the probability that the time elapsed between 2 events is greater than 2? Well, pretty damn low, I would say. Yeah, so, and that makes sense, 0.25%, right? Because it's supposed to be 3 events per second. It's very unlikely you're going to have 2 events separated by more than 2 seconds, right? So that passes the, the sanity test, I think. So the exponential distribution is kind of nice because the variables, it has this sort of memoryless property where observations are independent of one another. So you get these properties like if you've got n exponential random variables with n different rates, then the minimum value of all the variables is exponentially distributed with rate with the sum of the rates. Now this is a little bit confusing, I think, though, when you think about it, because if you go online, I don't want to go, try not to deviate too much here, but if you go online and you have let's say you have 2 normally distributed numbers, 2 Gaussian variables, normally distributed variables, right? Gaussian. If you add those, you get another value with where you add the means together. So if the mean is 2 and the mean is 4, you add them together, the mean of the sum will be 6, okay? But with the exponential distribution, if you have 2 exponential random variables and you add them, you do not add the gammas. Doesn't work that way. It's actually more complicated than that way. In other words, if you add the values of exponential random variables, you do not add the gammas. It's not how it works. However, this is not what this is talking about. That's not what I'm talking about in this slide. What I'm talking about in this slide is the minimum value. The minimum value of a set of random variables, exponential random variables, is itself a random variable with a rate in which is the sum of the rates. Now you might say, what's the difference? Well, the difference is if I choose 2 random values and add them, or if I had the sum of 2 random variables, that gamma of that value of the resultant sum is, I actually forget how to calculate it. You can look it up, but it's complicated. It's you have to derive it. You have to run it through an equation, whereas this is just saying the minimum. So I just want to point that out. We're not talking about adding variables. We're talking about finding the minimum of a set of variables. Okay, so anyway, and that's obviously, and you might say, why do you bring this up? Well, because at least in this course, we're not going to be having to add random variables. We're looking, generally speaking, we're looking for the minimum of a set of variables. Okay, so anyway, so if, for example, if you have 10 random variables, T1 through T10, they have gamma 1 through gamma 10. In the example, the gammas were the same. It was 0.1, so I can just multiply that by 10 to get 0.1, and that will be the gamma of the random variable representing the minimum value of those set of 10. So that's pretty cool, I think. So here's a way to apply that. Like if you have a bus arrives with an exponential distribution of 20 minutes, taxi arrives, an exponential mean of, sorry, bus has an exponential mean, 20 minutes, taxi has an exponential mean, 5 minutes. To get the gammas, you have to take the inverse of the mean, and then if you add those two, so this would be 1/20th plus 1/5, the answer is 1/4, and so the minimum, the random variable that represents the minimum waiting time between those two would have a rate of 1/4, and so then you can calculate that to find how long you can expect to wait for either a bus or a taxi, whoever arrives first. So in this case, you want to use the CCDF, the complementary. Although I mentioned this last time, the wording is a little bit imprecise. I said at least 5 minutes. So technically, at least 5 minutes would be saying, like, what is the probability of the value being greater than or equal to 5? Whereas I use the CCDF, which is the probability of t being greater than 5. So it's a little imprecise, but I just went with the CCDF here. So the probability of the waiting time being greater than 5 minutes would be, in this case, 29%. Okay, then let's see. I talked about the Poisson process last time. The Poisson process is, I really don't know how to explain it. It's like almost a variation of the exponential distribution. It's built on top of it, but the difference is between an exponential distribution and the Poisson process is simply the Poisson process gives you the probability of a certain number of events, occurring by a certain time with a certain rate. So Poisson is kind of like a counting version of the exponential distribution. So an example of this would be if you have a Poisson process with rate gamma equals 5 per minute. Notice I changed the time units here from seconds to minute. That's fine. It's just its rate is events per unit time. What is the probability that exactly 2 events occur by t equals 3? So you just plug in gamma and for, what is it, 5 for gamma? Yeah, you don't have, that's the gamma, that's not the mean. So yeah, you plug in 5 for gamma and you plug in 3 for t. So that's 5 times 3 to the second power over 2 factorial times e raised to the negative 5 times 3 is 0.0034. That's awfully small. But then again, remember, this is exactly 2 events occur by t equals 3. So we got rate 5 per minute. That's pretty fast. So you would expect in 3 minutes, so t equals 3 is going to be minute. I mean, obviously, I didn't say it, but it's implied it's minutes. So we would expect if you're getting things at 5 per minute and you're waiting 3 minutes, probably like, 15, right? Right? 15 is what you'd expect to get, right? But what's the probability that 2? Well, 2 is a much smaller number than 15, so that's why the probability is so low, 0.0034%. And then, of course, Poisson processes like the exponential process are memoryless. So it doesn't matter, what interval, any 3-second interval will work. And then if you're looking for the probability of 2 things occurring, you would, multiply. So what's the probability 2 events occur in one interval and 2 events occur in another interval? You would multiply those together, which would be a really, really small number, because we know that just the one of those terms would be 0.0034%. So now we're going to square that essentially. So I didn't show the answer there because it's very small. Okay. In a Poisson process, the times between successive events are independent and exponentially distributed with rate gamma. Well, what does that mean? Well, that just means what I just said. The Poisson process is just a counting version of the exponential distribution, basically. Okay, so this is where we left off last time. So one of the things you're going to want to know is what happens if we have events coming into a system and then being split off. Now, I mentioned in the beginning of this lecture that we're not going to talk about having multiple servers. So obviously that's what this is about, right? But not really. We're actually going to still apply this even in this class. But you can kind of see where we're going with this is like if you have multiple servers, you want to be able to, you might have multiple requests that are kind of earmarked for a certain server, and then we have the splitting that happens. So so suppose each event comes in, it's labeled with labeled an I type event with a probability P sub I, and that has to be independent of all else. Let n sub I of t and then I 1 to n be the number of type I events by type t. But so basically we have n of t, and then we have n1 of t and n of t. And so the idea is we're taking n of t and we're splitting it into n, I don't know, like sub-Poisson processes. But the deciding factor is determined by a probability. So basically what that means is you think of it like requests coming into a shared I squared C channel, but each of those requests want to go out to a separate peripheral. So then you look outside the I squared C channel, and you can then model the stream of requests coming out to each individual peripheral as these other split Poisson processes. And so what is the point of all this? Well, the point is that this is actually a very simple thing to do, because basically all you do is you take the probability of each one of those guys and you just multiply that by the rate, the original rate. So for example, if we have a Poisson process with rate lambda, and there's a 75% chance that the event will be type A and a 25% chance of being type B. Okay, so there's two classes. Then this would be equivalent to having two Poisson processes, A and B, having rates 0.75 times lambda and 0.25 times lambda, respectively, right? So so in this case, the two A and B would be independent. That means that the probability of the first Poisson process, A, generating, say, like 5 events by time by time 10, say, right, would be the same regardless of how many events you observe being generated from Poisson process B, right? So okay, so the opposite of that is superposition. And so this is another property of Poisson processes, and this relates the rates of a set of Poisson processes generating events and a single process that would basically absorb all of those events or generate all of the events from the set. So, for example, if you have customers entering from 3 separate doors, and they come in those doors with a rate of lambda, but then once they get in, they enter a single line, then that line will see arrivals with a rate of 3 times lambda. Well, it's kind of common sense, right? Did I hear a ping? Is there a specific confidence interval being used for calculating these probabilities? No, I don't know. The confidence interval is, I think that would relate to if you were actually observing, like if you were calculating the probabilities from the data, if you were doing an empirical measurement, if you were, like, and I'm assuming that we're given these probabilities and that they're 100%, they're given to you, as opposed to measuring the number of occurrences and using those to calculate the probabilities, in which case you would need a confidence interval. But you know, because if you were measuring the probabilities, you would have to have a, you know, a statistical significance. But in this case, I'm just giving you the probabilities, right? So it's a, you know, it's a given, right? So no, there's no confidence, confidence interval here. And the reason, by the way, you might say, well, where's all this going? I mean, what's the point of all this? Well, the point of all this is these are the things you need to know in order to derive the numbers for a given queuing system. So these are like basically the tools that you're going to use to be able to get to infer things about these models, these queuing system models. That's where we're going with this. So eventually we're going to use all this stuff to basically calculate the waiting time of an MM1 queue. So that's where we're going, just to kind of give you context here. You know, this isn't just I'm not going through all this because just for the excuse of going through this mathematical exercise. This is essentially how you analyze queuing systems. It's kind of a manual process. Now, once we get done doing that, then there's some kind of just baseline equations you can use for an MM1 queue. But then if I throw you a curveball and modify the MM1 queue, then you have to go back and kind of derive this stuff again. That's kind of the premise of the queuing theory. Okay, so let's see. Events in a Poisson process are independent. I think I talked about that. Okay, so here's an example of what I mean by this independence thing. People arrive to a security center at an airport according to a Poisson process. The security center has two lines. An agent at the entrance assigns each arriving passenger to one of the two lines. This is done in an alternating fashion, right? Makes sense. Just every time someone arrives, you send them to the other line. You know, even numbered arrivals go to the left queue, and the odd numbered arrivals go to the right queue. Are the arrival processes to each queue Poisson? No, they're not, because the queue assignment of passenger J depends on the queue assignment of passenger J minus 1. That means they're not independent, and so the individual queues do not behave as Poisson processes. However, if the agent were to randomly flip a coin to determine the queue assignment, then the arrival process to each queue would be Poisson, because technically you would still get half on each over the long run, but it would qualify as being a Poisson. So you can analyze it as a Poisson process. Okay, so now we get into sort of the more rigorous part of this. Okay, so so the way that you analyze a queuing system is generally done, I mean, there's different ways you can do it. There's different strategies, but one way to do it is through a birth-death process. A birth-death process is a type of Markov chain. Now, the textbook for this course, the queuing theory course that I took the material from, has like a whole chapter on Markov chains. But most of that stuff is not really, you know, they talk about generalized Markov chains. Most of that stuff is not really applicable directly to this stuff. So I've chosen instead to just focus on this one particular type of Markov chain, which applies to a queue, which is a birth-death process. So the number of requests in a queuing system, in this case, now again, we're talking about a queue system. We're including the queue itself and the server, because requests can be in the queue or they can be being serviced, but either way, they're still in the queuing system. It's often modeled as this birth-death process. And this is the way I'm showing it here. You might look at this and say, well, this looks like a state machine. This is a continuous Markov chain, which is basically a state machine. But the way it works is this. Well, first of all, how is it like a state machine? Well, it's like a state machine in the sense that a system can only be in one state at a time. Now, by the way, if you don't know what I'm talking about when I say state machine, that's okay. State machines are something that you would study in digital design, but for some reason they don't cover it very well in our 211 course. State machines are also used in compiler design to do lexical analysis for compilers. State machines would also come up in a theory of computation class, but you might not have taken any of these yet. So don't worry if you don't know what I'm talking about. But basically, and we're going to talk about state machines later this semester. We'll get to those too as well as they relate to digital design and protocol design. But at the moment, just take it this. If you're not sure what this, if you don't experience with state machines, state machine is a machine where the machine can be in one state at a time. So in this case, we can be in a queuing system can be in one state that represents the number of customers in the system. That's why they're numbered, 0, 1, 2, 3. So you can be in any state that represents where you are. Now you'll notice that each one of these states has two arrows coming out. One arrow takes the state number one higher, so you can go, for example, from 2 to 3, and the other one goes one lower, which is 2 to 1. You can't skip. You can't go from 2 to 4 or 2 to 0 because we're assuming that only one, the number of elements in the system can only change by one, because we're assuming that only one value can enter at a time, only one only one customer can enter at a time, only one customer can be serviced at a time, and you can't service and enter, a customer can't enter and another one be serviced exactly at the same time. Why? Well, because it's a continuous process. So again, it's continuous, meaning that there's an infinite number of values even between, an upper and lower number. So there's no way you're going to have, someone come in at exactly the same time as as someone finishes, right? So that's why we can basically go up by one or go down by one. Now, how do you go up or down? That's the question. Well, this is how Markov chains differ from state machines. In a state machine, you'll have an input that determines when you change states. But in a Markov chain, changing of states is random. It's stochastic. So transitions can occur at random times, but the time at which a transition occurs is a exponential random variable. In this case, is an exponential random variable. And the rates of the exponential random variable are defined on the transition. That's why we have lambda and mu. Lambda is the rate at which new customers enter, and mu is the rate at which new customers depart. Now let's think about this for a minute here. Remember that these are rates. So in a queue, as I mentioned, you can't have customers entering faster than you can service them. It's just not allowed. So that means that lambda has to be strictly less than mu. Has to be. Otherwise, this thing just blows up, right? So keep that in mind when you talk about lambda and mu. Let's see, anything I'm forgetting here? Yeah, so I mentioned that there's two transitions exiting each one of these guys. There's two transitions entering. Now you might be thinking, oh, wait a minute, I've got two transitions exiting. Both are based on a exponential random number. So that's kind of like the splitting. Well, okay, so I have it written down here. So remember that not splitting, sorry, the property that says that if you have n random variables with rates lambda 1 through lambda n, then if you're looking for the minimum time, that's another exponentially distributed random variable with a rate being the sum of all the rates, right? Okay, so let's talk specifically about this then. You have two random variables, one with rate lambda, one with rate mu, that represent two exiting conditions from a state. What that means is the time that you spend in any one of these states is then therefore a exponential random variable with rate lambda plus mu, right? Does that make sense? Now that's with a very important exception. State zero. State zero only has one exiting transition. You can't have less than 0 customers. So state 0 is an exception here. But for any state that's not 0, you have lambda coming out, you've got mu coming out. Lambda is adding a customer, mu is subtracting a customer. So you can expect to spend lambda plus mu, or the amount of time you spend in a state is expected to be a random variable with rate random lambda plus mu. So now you can see how now we're applying this property of exponential distributions. We're applying this property to this birth-death process. Okay, just double checking. Right. Okay. Okay. So also we're going to associate a value p of n being the probability of being in state n. You can think of this, by the way, as the percentage of time you spend in state n, right? Because so if the probability of being in state 2, which would be p sub 2, if that's 20%, you can expect to be in state 2 20% of the time, right? Now, the thing about this that's a little confusing, at least to me, is that we're talking about probabilities now, but we're mixing probabilities with rates. So you've got p of n that's associated with each state, but then you've also got lambda and mu, which are not in and of themselves probabilities. Those are just rates that you would have to then run through the exponential equations to then get probabilities, right? So keep that in mind. I don't want to, you have to keep these concepts separate. Okay, so I mentioned the steady state earlier. So steady state, one of the things to describe that a little bit more precisely, steady state means that the rate of transitions out of a state equals the rate of transitions into the state. This is something I think is a little bit hard to get your mind around. Okay, so let me back up here a minute. So queuing systems are generally assumed to operate in steady state, otherwise they just blow up. In the long run, I mean, when I say in the long run, I mean they stabilize over time. It's not instant, because when you first start running these things, they kind of bounce around. But then eventually, as long as they're stationary, they will eventually reach equilibrium, which basically means that the number of customers you get in the queue stabilizes and the delay of the whole system stabilizes. So the steady state means that the number of requests will stabilize around a particular number of requests in the system, number of customers, whatever. This is similar to the stability that we talked about in control theory. It's very basically the same idea. So now this part is a little weird, because the rate of transitions into a state equals the rate of transitions out of a state. I don't really see how those two things relate to one another, but basically without that property, the state number would be unbounded and it would increase infinitely. So now you might say, well, wait a second, hold on. If you reach equilibrium, you're going to probably end up in like one state, right? So obviously the rate into that state and out of that state should be equal, but why does that apply to all states? It has to be, well, because you don't know exactly what state you're going to end up in when you reach equilibrium. So the rule is that the rate of transitions out of a state equals the rate of transitions in, right? So just understand that. So now the problem is that you have two transitions coming out of each state, but you also have two transitions coming into each state. And again, this is except for state 0, we handle that one separately. So, so you have to then use the splitting property sorry, sorry, back up here. You're going to use the superposition property to multiply the rates of the two transitions entering the state from states n-1 and n+1. So if I'm state n, I've got incoming arcs, incoming transitions from the state before me, n-1, and the state after me, n+1. And so I am going to multiply each of those by their corresponding rates, which are going to be lambda if it's coming up from n+1, or mu if it's coming down from it's lambda if the transition is coming into me from n-1, because if I'm in n-1 and I get a lambda, that means I got a new customer, it's going to come up. So incoming transition from state n-1 is lambda. Incoming transition from state n+1 is mu. And so then I would multiply those rates by the probabilities of each of those states. Now you might say, wait a second here. Wait a second. I thought you said the superposition property was a property of the Poisson process. But now you're applying it to the exponential distribution. Yes, yeah, it works that way too. It works the same way, right? So we can take the rates and multiply it by the probabilities, which I just said. Remember, make sure you're keeping these ideas separate. You've got rates, you've got probabilities. But because of this superposition property, you can multiply the probability of the states before and after by lambda and mu, and that's going to give you basically the flow into the state n, right? Now you say, what do you mean flow? Well, flow in this case is the rates times the probabilities. And then I'm going to equate that to the outgoing flow, which is mu plus lambda times p sub n. So the probability of state n multiplied by the sum, and this is now I'm using the splitting property to multiply the sum of the outgoing rates of state n with the probability that the system is in state n. So that's mu plus lambda times p of n. So basically, I'm going to equate. I'm going to set these two values equal. The flow out of state n needs to equal the flow into state n, which I obtain by there's three probability values involved. There's the probability of state n, and then I add up the mu and lambda, which would be coming out of state n, multiply that. And that's equal to the probability of coming in from n-1, which is lambda, and the probability of coming in from state n+1 times mu. So those have to be equal. This is a basic property of the birth-death process and as it relates to the queuing theory. Okay, yeah, I know it's a little strange. At least it is to me. But this is the basic equation that we're going to start with in order to analyze this thing. And again, this applies to states having two incoming transitions. So how do we deal with state 0? State 0 has no incoming transitions. So it's actually simpler. We just have to equate the one incoming and one outgoing with state 0. So there's an outgoing state from state 0, which is our lambda rate, and there's an incoming from state 1, which is our mu rate. And again, remember, lambda is increasing state number, mu is decreasing state number. And by the way, this is a little bit misleading because remember the exponential parameter is lambda, and we have a lambda, but we also have a mu. Well, mu is also a lambda for the service distribution, right? It's kind of weird. I would have just, I don't know. I think it's a little confusing, the fact that we've got a lambda and a mu, but both of these things represent a rate, right? So we just have two different rates. Now, as you might imagine, by the way, you can have different rates coming out of every state. You can have different, you can have different lambdas and different mu's, but in this case, we're assuming that there's a single mu and a single lambda that represents the incoming and the outgoing rate of the system, which is the arrival rate and the service rate, okay? So you don't have to worry about they're all the same mu and lambda. There's only one mu, there's only one lambda. Lambda is the rate at which new customers arrive. Mu is the rate at which we can service customers. And again, keep in mind too that lambda has to be less than mu or the whole thing blows up. Yeah, yeah, that's right. Yeah, they're both rates. They're both rates. Um, they're both rates. They're both rates in terms of the exponential distribution, but they have different letters, and one is the arrival, one is the completion, and the arrival better be less than the completion rate, or the thing just will blow up. Now, again, though, when you think about it, like, well, wait a minute, if that's true, this shouldn't be a hard problem at all. I should just be able to service everyone right as they show up. But again, it turns out not. Hopefully I'm gonna convince you that that's not how queues work. Okay. So again, though, let's go back to the main questions here, because I want to try to maintain. So it's kind of hard to, it's easy to get lost in the math. And I don't want you to get lost in the math. We have to stay on target. We got to know our objective? What are we trying to solve for here? Waiting time, number of customers that may accumulate, and the idle time of the servers. Those three, why is there an extra colon there? Sorry. Anal about that. Those are the three things we care about. We want to know, as we increase the rate at which we make requests to a hard drive, how is that going to affect our latency to the hard drive? So this is an important relationship now between throughput and latency. How many customers may accumulate and the idle time. Now, you might have noticed here that the waiting time is a parameter of Little's law, as is the number of customers in the system, right? The only thing we're missing here is the arrival rate, which of course is lambda, but that's usually a given. And then of course mu, which is also given. Okay, but again, we want to know waiting time, we want to know how fast this thing is, and we want to know how big it has to be. So we want to derive 4 things in this class. Now, in a real queuing theory class, there's a lot more you can derive here. There's a lot more analysis you can do. But for our purposes, we just want the big ones. L, number of customers. L sub Q, number of customers in the queue, just the queue, not the ones being serviced. W is the expected waiting time, and then the idle time. And the idle time is just the probability of being in state 0. There's no customers there. Likewise, state 1, by the way, would be the amount of time that you have one customer in the system, which is going to be, obviously, if you have one customer, you know he's going to be getting service, which implies that the queue is empty. So you can infer things like that based on the probability of the individual states. You can also figure things out, like you can solve for anybody that's in the queue, like if there is any waiting involved, how long do you have to wait? But to be honest with you guys, I couldn't figure that one out. That one was a little bit over my head to derive it. I mean, I could look up the equation, but I want to be able to know how we get the equation, and that one was kind of tough to figure out. But these ones are a little easier. These are the main ones. Okay, so let's derive first. We want to derive the probability of being in state n. You might say, why do you start with that? Well, I'm starting with that simply because the only equation we really have, aside from Little's law at this point, is our flow balance equation, which is the flow balance is just the lambda plus mu times p sub n is equal to so basically your arrival flow, your flow coming out of state n is got to be equal to the flow coming into state n, which is defined by this equation, and of course it's only valid for n greater than or equal to 1, because this doesn't work for state 0. So so let's start with, what do we do first here? Let's rewrite this equation and isolate p sub n plus 1. Why? Well, as good a place as any to start. So p is basically, just rewrite this using algebra. P n sub n plus 1 is just going to be lambda plus mu over mu times p sub n minus lambda over mu times p sub n minus 1. So this is just literally just rewriting the top equation, which we gave you as the flow balance equation. Okay, so now, so let's, this part's kind of cool. So where do we go from here? What do we do? Well, actually, if I hadn't had some help from the book, I probably wouldn't know what to do. But the way to approach this is to just take some numbers and put them in for n. So instead of using n, let's set n to 1. And so n plus 1 would have then, of course, be 2, n would be 1, and n minus 1 would be 0. If you do that, then you get an equation here that's a little bit more concrete. You get p sub 2 equals lambda plus mu over mu times p1 minus lambda over mu times p0, right? It's just basically just the same thing we had before. It was the flow balance equation. We rewrote it to put n plus 1 on one side. So we were calculating the probability of n plus 1 as a function of the probability of p of n and p of n minus 1. And then we just simply set n to 1. And so now we have, this is where we are. Now we know that the probability of being in state 0, we can calculate the, oh, sorry, I got the animation order wrong here. I previously gave you the equation, the flow balance equation for state 0 is lambda p0, which is the probability, the outgoing flow for state 0, has to equal the incoming flow of state 0, which is mu times p of 1. You can p sub 1. You can rewrite that equation by putting p1 on one side by itself. And of course, if you do that, you have p sub 1 equals lambda over mu times p sub 0. And then you can substitute in p sub 1. You can put that back in the equation on the left, right? You just take this and substitute it in here. And so by doing this, we knocked out p sub 1. So we went from 3 variables to 2. Well, that's good. And then if you use some algebra here and multiply this guy out, now this is interesting, right? Lambda lambda plus mu lambda over mu mu times p sub 0. But how do we combine this all into one term? Well, you have to, we'll do like we did before, where we'll multiply this term by mu over mu, right? So that way we'll get lambda mu over mu mu, and then we'll have a common denominator, right? Okay, so there's our common denominator. Now once we have this, we can just combine these into one term, which conveniently, it's subtract mu lambda, and we have mu lambda here, so this will actually delete mu lambda. It'll cancel out mu lambda. So we end up with is lambda lambda over mu mu times p0. Well, that's really nice. Look at that. Okay. Well, now we have p2 as a function of p0. We've not only have we knocked out p1, but the equation itself is real simple. It's just lambda squared over mu squared. That's pretty nice. Okay, so now let's set n to 2. So go back to the original flow equation, and just increment all our subscripts. So now we have p3 equals lambda plus mu over mu times p2 minus lambda over mu times p1. And as you can imagine, we're going to take this new guy here, this p2 equals lambda squared over mu squared p1, just substitute that in, and of course we're going to get the same kind of effect as we got before. Oh, sorry, and also p1, sorry. p1, we also have to include, substitute in this p1 as well. And now this guy distills down to lambda cubed over mu cubed p0. Okay, so now again we have another equation here where we can relate the probability of state 3 to the probability of state 0. Of course, you could see a pattern forming here, right? It's not too hard to see that basically the probability of being in any state is simply going to be lambda over mu to the nth power times, where n is the state number, times the probability of being in state 0. So, I mean, you can just generalize that. I mean, you can see that, you can keep going with this. This ends up becoming kind of a recursive derivation. It's inductive. But yeah, it's basically, lambda over mu to the nth power times p sub 0 is the probability of being in state n. Okay, so now that's obviously that's not real helpful yet, though, because we still aren't. Again, what are we looking for? We want to know how many customers are in the system. So we want to know the expected state, like what state do we expect to be in? What's the average state we'll be in, right? Expected state number, and we want to know the delay, how long it's going to take to get through. And this doesn't really serve that purpose. It's cool. I mean, we know the probability of being in state n, but doesn't really help us yet. And also, we don't know the probability of being in state 0, so that's kind of a deal breaker right there. I mean, if we don't know p sub 0, then we can't get p sub n, even if we have a cool equation for it. So that kind of stinks. So what do we do? Well, we take advantage of some basic probability knowledge. We know that if you add together the probability of all the states, it should equal 1. Why? Because you can only be in one state at a time, right? That's just a rule of a Markov process, or of a deterministic state machine in general. You can be in one state at a time. So the probabilities, if you add up all the probabilities of all the states, it should equal 1. The problem is that there's an infinite number of states, because you could have, well, I mean, the system capacity is infinite in an MM1Q. So that's inconvenient, but we have to add up all the p's of n from n0 to infinity, and that should equal 1. Well, the good news is we have a definition for p of n, which is not a definition, but we've derived p of n. We can substitute in p sub 0 times lambda over mu to the nth power. So that's good. So that makes things a little easier. Okay, so let's, first of all, we need to simplify this a bit. So lambda over mu, let's set a new term called rho and substitute in rho. Why are we doing this? Well, for convenience. It's just because convenience. This is only for the math. That's why we're doing this. We don't want to have to deal with lambda over mu. Just substitute lambda over mu is now rho. Now, this was a very poor choice, by the way, rho. Rho is a Greek letter whose lowercase form is indistinguishable from a lowercase p. Why would they do that? Why do we have p's and rhos together? They look the same. They almost look the same. They look a little different, but could they picked a better letter? I don't know why we make our lives more difficult than they need to be, but that's rho. By the way, rho, just as a so I always remember rho as a I always remember what rho looks like, because I used to work with a guy who was a stoner, and back when I was in undergraduate school, and he had a bunch of stoner friends, and none of them had jobs, only he did. And so he would be the only one that would have the ganja, and so he, that gave him power over these guys. So like anytime he would break out his supply, he would scream "Row," and they would all come running, almost like Pavlov's dog. Because and I asked him, I said, "Why do you say row?" It's like, what does that mean? Row, row, row your boat? What is that? And he says, well, row is a P. It stands for pot. And that's why they knew to come when he would scream row. So that's how I always remember what row is. But anyway, so row is the ratio of lambda to mu. Remember, though, that I said that lambda has to be less than mu. So basically, rho would be a value between 0 and 1, not including 1. So less than 1, greater than or equal to 0. So that gives you an interesting thing happens when you add together a bunch of numbers that are between 0 and 1. Sorry, when you add together powers of numbers that are between zeros and 1. Sorry, I forgot about the n exponent. Sorry. So when you take a number between 0 and 1 and you bring it to power 1 and you add it to its power 2 and you add it to its power 3 and you add it to its power 2. Now normally if this was any old number and you did this, you would expect it to just blow up to infinity, right? I mean, you're adding together a number plus the number squared plus the number cubed plus the number to the 4th power. You add those up and it's just going to get really big really fast, right? But if you do that to a number between 0 and 1, greater than or equal to 0 but less than 1, you get this cool mathematical relation. And this, by the way, this comes up really frequently in my experience, and I'm not even a math guy, but I see this all the time. So if you do this, you get 1 divided by 1 minus rho. Now you might be thinking, why? Where do you get that? Where does that come from? Well, it works. So like if you do an example, like set rho to 0.5. 0.5 divided by, like if you take the equation that's there, that I take this as a given, right? 1 divided by 1 minus rho. So if rho is 0.5, 1 divided by 1 minus 0.5 is, I'm sorry, wait, I got that right? Rho? Yeah. Wait a second, did I screw this up? No, that's right. Yeah. So so let's take like I said, 0.5, and you say 0.5 plus 0.5 to the 2nd power. Actually, well, you start out with you start out with 0.5 to the 0th power, right? Which is 1, right? And then then you add 0.5 to the 1st power, you add 0.5 to the 2nd power, you add 0.5 to the 3rd power, you add 0.5 to the 4th power. You keep adding those up. You're basically going to converge on 2, right? So you're going to have 1 plus 1.5, 1 plus 0.5 plus 0.25 plus 0.2575, or sorry, 1.125, right? You just keep adding. You're gonna keep adding those up infinitely. You're going to get to 2, right? And that makes sense because I'm saying 1 over 1 minus 0.5 would equal 2, right? So as long as your rho value is less than 1, it's got to be less than 1, and I think it's got to be greater than or equal to 0 too, right? Then this summation is going to give you this magical 1 over 1 minus rho. Or any variable. It doesn't have to be rho, obviously. Any when you do this for any variable, it sums up to 1 minus 1 over 1 minus rho. Now, if you've never seen this before, this is a good thing to memorize because, like I said, I've seen this come up a bunch in different fields. This relation. Okay, so where are we at here? Let's get back to the story. So basically, I converted this to rho. Also notice this P0 term, I moved this outside the summation. Why? Well, it's not a function of n, so you can do that. All right, so P0 is invariant of n, so I could move that outside the summation, and then I was left with just the summation from n0 to infinity of rho of n. This is equivalent to then 1 over 1 minus rho. This is just a mathematical thing that comes up a lot. You just kind of have to recognize that, and that's what comes up. Okay, so now we've got this thing, which is what I previously showed, and now we have to go back. Now this is where this is where things get a little weird, because now you have to remember where we're going here with this. We're going with 1 equals the summation of all the of all of the probabilities of all the states should add up to 1, right? Okay, so we're going back to the original equation here. So yeah, this is the original equation. 1 equals p sub 0 times, yeah, these guys all up. And so remember that this entire summation thing we determined is actually equivalent to 1 over 1 minus rho. Of course, the p sub 0 stays there and the 1 stays there, right? So we do some algebra. We multiply both sides of the equation here by 1 minus rho, and 1 minus rho then would equal p sub 0. Well, that's cool. Wow. Well, we finally have p sub 0, 1 minus rho. And what's rho? Well, that's a value we can readily get, because when we design the queuing system, it's assumed that we know the arrival rate and the service rate. So if we know those two, the ratio of those two is rho, and all we have to do is say 1 minus rho, and that's the probability of state 0. That also gives us the probability that there's no customers in the system. Well, that's pretty cool. Now we're getting somewhere. I think that's cool. I like that. And from here, we can keep going and find those other variables too. But I'm going to stop here because I've only got 4 minutes left, and it's going to take me longer to get through that, and I don't want to get carried away and then have to just stop. So, and plus, I want to give you guys a couple minutes. I mean, only 4 minutes, but give you guys a few minutes to take a look at the quiz. Again, you can open the quiz without penalty because you can leave it open as long as you want, unlike the exam. The quiz is on queuing theory. This will give you an idea of the questions that I will ask not only in the quiz, but they're basically very similar questions will be on the exam. So that'll give you a really good idea to see where I'm going with this and what I'm going to ask, and you know, then you can use that as kind of a context as we finish out this queuing theory lecture on Monday, and hopefully we finish it on Monday. Okay, and also keep in mind that we've got the first lab is due, I think, next Friday, right? Which is the 19th. Yeah. So the quiz 2 will be due on the 17th. Sorry, quiz 5 rather will be due on the 17th, and the project 2 will be due on the 19th. So you're going to have 2 dates that are within 2 days of each other. So just keep that in mind. I don't want you to get caught off guard with that. So keep that in mind. I suggest you open up the quiz, check it out. Let me know if you have any questions. If you see any typos, please let me know. You know, anytime we do these mathematical quizzes, there's bound to be typos. And if you find any, let me know. I'll fix them right away. Okay, I guess then I will see you guys on Monday. Have a good weekend. And as always, let us know if you have any questions about the material or the project. Thank you.